Good morning, good afternoon, good evening, mammals. This video is for NTI day number 5, Tuesday, March the 16th. On Friday, I left you with a packet of notes, and that's going to be going through these. If you happen to lose those, I'll be sure to post a PDF copy of them in Google Classroom. What we're going to be talking about today is the main factor that we're going to use to explain all of these different properties we're going to be looking at in this unit. So we're going to be talking about something called effective nuclear charge today and deciding whether it increases or decreases as we go up, down, left, right on the periodic table. But before we do that, we're actually going to go kind of on a detour about the history of the periodic table itself, and I'll try and be super brief about that. So, periodic table comes from the word periodic, which means things that happen in a pattern. So, Pascal's triangle, predator-prey cycles, sine waves, engines, all of these things happen in cycles that are said to be periodic. But what is this repeating cycle on the periodic table? So hopefully you know from our last unit that the electrons on the periodic table come in a repeating pattern, 1s2, 2s2, 2p6, and that just repeats and builds and grows on each row of the periodic table. However, I think what's interesting is the periodic table was developing this kind of modern shape, this, the shape that we recognize as coming from the electrons even before people knew what electrons were. So that's going to be our history lesson. The first person to put the elements in a table rather than a list was a Russian chemist named Dmitry Mendeleev. And what he did is he started putting the properties of each element on cards and basically doing a card sort to try and get these properties to repeat in an orderly fashion. And so when he arranged the elements so that the properties repeated in each row, he found that they were actually in order of atomic mass. So he could sort of shorthand this repeating pattern of properties just by putting them in an order so that the atomic mass increased each time. Now what he really gets credit for is these blank spaces. If he didn't have an element that fit the pattern, he left it blank. And I think like a lesser person would have put the thing that fit the closest that he had available to him into that spot. But Mendeleev said, these are actually going to be undiscovered elements. If I don't have anything that fits this pattern, there's going to be something out there that hasn't been discovered that will. And he went on and predicted their properties with considerable accuracy. So we can see, here's what he called the elements. He named them after the nearest element that they knew about. And then when it was actually discovered, you can see that the properties actually line up pretty well. So his pattern was working very nicely. Fast forward a few decades, and the protons have been discovered, and this allows Henry Moseley to improve on these patterns by arranging the elements according to atomic number, because now they know about the number of protons. And there are a handful of elements where the order gets switched, where the atomic number goes up but the mass number goes down. And so it actually improved on the pattern that Mendeleev has. So that's Moseley. So the things that you need to know that might be test material for these guys is Mendeleev. He's arranging his according to properties and atomic mass. I think the better answer is actually the properties, because he put them in order of properties first and then just noticed that it was in order of mass. And then Moseley protons been discovered, and he puts them in order of atomic number. The blanks, undiscovered elements. Elements, and you got to have the proton to put them in order. And so that's the end of our history lesson. I'm going to move on to the main topic to keep this reasonably short. Short as possible. Still going to be a whole set of notes. Okay. So you need to don your logic caps to sort of think about this. Previously, we've written the electron configurations of elements. So I just picked an element, germanium, on the periodic table. And there's its electron configuration. So to give you some reference on the periodic table, bad sketch there. Germanium is about right here. So that's where we're talking about. I just picked somewhere in the middle. And I hope you can see from this, there's its electron configuration. And I turned it into this diagram. We've got the protons, the neutrons. I've got the 2 electrons in the first shell. I've got the 8 electrons in the second shell, the 18 electrons in the third shell, and the 4 electrons in the fourth shell. Now, electrons are attracted to the nucleus, so we've got an attraction force between the valence electrons and these protons because they have an opposite charge. However, we've got a repulsive force from these inner electrons because they have the same charge. So all through this, we're going to be making kind of a comparison between attraction for protons and repulsion, if I can spell, repulsion for inner electrons. And the key thing to note is we aren't going to consider the valence electrons. These guys, they don't matter for the repulsion, because if I'm this electron here, this valence electron, and I'm looking at the nucleus, the inner electrons are in my way and are causing repulsion. These other valence electrons, they're sort of on the same level as me. They aren't interfering with my ability to be attracted to the nucleus. So we're only going to be considering number of protons and number of inner electrons. So let's make some comparisons. The effective nuclear charge, our main goal, is the amount of attraction that an atom feels for its valence electrons. So what I have to consider is I have to consider the attraction from the protons, and I have to sort of subtract out the repulsion from the inners. So that's kind of the logic step that I'm doing here. So I'm going to make a comparison now. We're making a horizontal comparison. So sketch my periodic table here. So I was comparing GE, and now I picked BR. Same row. So on this page, we're making a horizontal comparison. Let's look at what is the same and what is different. The protons have increased. Okay, so we've got more attraction. More attraction. The inner electrons have not increased. 28 inner. Bromine has more electrons, but since it's in the same row, they've been added into the valence shell, and I don't really need to consider the valence electrons. All that I'm considering is that the inners are the same. So if I'm comparing two things with more attraction, but the same amount of repulsion, my overall force is going to be stronger. This would be like if I was holding up pieces of paper on the fridge and I ask it to hold two magnets to hold up the same number of pieces of paper. So they've both got like the same weakening force from the paper. But one magnet is stronger. It's going to be clinging to the refrigerator with a greater force. So effective nuclear charge, the takeaway here is that effective nuclear charge increases as you go to the right. So going to the right, ENC gets bigger. If you're kind of a mathy person, what I'm doing here is I'm taking my protons, my positive force, and I'm dividing it by my repulsive force. So GE, 32 attraction, 28 repulsion, is smaller than 35 with 28 repulsion. Okay? Now we're going to compare vertically. So on the periodic table, I'm making a comparison here, still using, ooh, that's ugly. Try that again. I don't have the greatest stylus here, so bear with me. So I'm still working with GE, but now I'm comparing it to the atom beneath it. So we're making a vertical comparison. Can't spell. All right, so let's look at our differences. Our protons have, that's not what I wanted. I wanted the pin. There we go. Our protons have increased. So attraction has gone up. However, this makes things a little bit more confusing. Our inner electrons, our repulsion, has increased also. So attraction has gone up, repulsion has gone up. But the repulsion has gone up relatively more. 28 to 46 is a larger change than 32 to 50. And you can see it in the ratios that I worked out. 32 divided by 28, 32 attractions, 28 repulsions, is a bigger number than 50 divided by 46. So what is happening here is the effective nuclear charge is decreasing as we go down. Because although the attraction and the repulsion are going up, the repulsion is going up more. So at this point, what I think is handy to help you guys organize your thoughts about this is to think about the periodic table in terms of corners. Okay, so effective nuclear charge increases as I go up, and it increases as I go right. So this is increasing and increasing. That means this element right up here, helium, has the highest ENC, the highest attraction for its electrons, and francium has the lowest. So if I have any sort of problem that asks me to compare elements in terms of effective nuclear charge, I'm going to be comparing them along this diagonal, and I'm going to be ranking them from highest to lowest. Okay, so I'm going to post some follow-up questions on a Google Docs just to kind of make sure that you've gotten the main things that I want you to take away from this. You can submit that inside of Google Classroom as verification that you've sort of watched and paid attention to these notes. And that's going to wrap it up for today. So, as always, take care of yourself and others, practice good hygiene, and I'll see you on the flip side.